Just Ian has provided multiple layers of support in developing several generations of Dr. Connors's internationally regarded geospace research projects and has played an instrumental role in developing Canada's foremost auroral observatory, the AU Geophysical Observatory at Long and Narrow Lake, Alberta. Ian holds a bachelor's and master's degree from the University of Lethbridge in computer science with extensive experience in instrument development. He and Dr. Connors have just completed developing a new generation of solar-powered space weather monitoring stations. Ian and his family currently live in Athabasca, Alberta. Welcome, everybody, and welcome, Ian, and over to you.
Okay. Well, I will start by sharing my screen as soon as I figure out how to do that. So let's start here. And this is the title of my talk, and this is a very accurate picture of what we know as the Northern Lights. So yeah, whenever you see them, you're supposed to run and hide because that means danger's coming. But no, seriously, this is a talk about the aurora borealis. That's an area of research that AU has been involved in for quite some time because, well, we're pretty close to them. But you'll discover that through the course of this talk, the auroras are not scary and certainly do not look like this picture. But it is fun to look at some of these, older historical accounts of what people thought they were. So anyways, you can hear me okay from here? Okay. Let's go on to the first talk, or the first matter of business, and that is about me. Thank you, Lisa, for the introduction. Again, I've been an observatory researcher at Athabasca University since 2007. And it's kind of hard to explain what exactly it is because for the last 15 or so years, I've done an awful lot of different things, but mainly it has been looking after and working alongside Dr. Connors with his many different projects that have involved online astronomy and auroral research, or as I'll continue to say, space research, which really involves studying the Northern Lights. So for sure, all these years I've worked along with Dr. Connors in developing and maintaining the observatories, the one here on campus and the one that's southwest of town. We've developed quite a number of different devices or systems here at AU. Myself and along with a number of students who have worked in our labs over the years. We've developed magnetometer networks since the day I started. There was a rudimentary network in existence, and we have been continuously building them. And the funnest part of being an observatory researcher is doing field work. And that is something that we've done nearly every year, with the exception of the pandemic years in 2020. We did sneak a little bit in 2021. But that's sort of been the highlight of this field. And unlike other sciences, with earth sciences, you really do have to get outside and dig in the dirt. And that really is a lot of fun. So I'm going to start here with a bit of an introduction, and this picture here will give you a clue about what we're talking about. This is actually not that long ago. This is back in September, I believe, and this was taken from my doorstep in Athabasca. So yeah, Athabasca is a place to be if you want to see some impressive light shows. Okay, first of all, space physics has really been an important area of research that AU has really excelled in. And one of the major reasons is that we have such a great location in relation to where auroras take place. Just to reiterate, when I talk about auroral science, I'm talking about the science of the aurora, and the broader, the bigger term that involves the aurora is space physics. And Dr. Connors has been the astronomy and physics professor at AU for quite some time, I believe since the 90s. Since the late 90s, he's been involved in doing experimental space research using a number of different types of equipment, but the two main go-to types of instrumentation that we've used have been magnetometers to measure the magnetic field of the Earth, and all sky cameras. And you'll be seeing quite a bit of that in this talk. So yeah, since the late 90s, that is what he has been involved in. And when I came on the scene, that's what I was working with. We've actually had the opportunity to work with some fairly prominent science endeavors. Probably the biggest was the NASA Themis mission, which was a space mission from 2007. And we had the opportunity to host some of their instrumentation at our Geospace Observatory, which was on campus. Maybe a little bit more whimsical, but also serious, is a project that was also a NASA project. It was more of an EPO, that's an EPO project, that's Education and Public Outreach project, called Aurorasaurus. And basically what they were doing there was crowdsourcing aurora pictures from people from around the world to basically report where they were seeing auroras. Basically asked you, did you see an aurora? How strong was it? Where did you see it? At what time? And out of this endeavor, out of this project, a new type of aurora was discovered, which has been termed Steve. And I'll get into that a little bit later on. But no, that is something that we were, somewhat indirectly involved in. But it basically came out of the advent of digital cameras and the availability, cheap availability of digital cameras to take gazillions of pictures. And eventually people discovered phenomenon such as Steve, which had been there all along, but nobody ever had the opportunity to, shoot, thousands of rolls of film would be a bit expensive. But once they opened up this project, the data started flowing, and then discoveries could be made. So anyways, I'll continue on here. So space physics. Okay. Why do we do it in Athabasca? Well, a picture is worth 1,000 words, and this picture is certainly worth 1,000 words. This is the real reason. It's because we are in such a good location. And again, to describe what it really is, the field of space physics is the study of the solar terrestrial environment. The way I like to explain it is the study of everything between the Earth and the sun, and how the sun affects that environment. And we certainly are affected, especially when we see light shows like this. We're quite familiar with terrestrial weather. That's everybody knows what that is. And that's ultimately, it is driven by the sun. The sun drives the seasons. It affects a number of processes on Earth, but it also affects space weather. And that is part and parcel of the steady stream of particles that flow off the sun all the time. That's called the solar wind. And sometimes that gets turbulent, and then when that happens, we say that there's a magnetic storm happening, and it manifests itself as the northern lights. And that's exactly what this picture is showing here right now. And we just happen to have a front row seat in Athabasca to actually watch this all. So yeah, the aurora is the most natural way that we experience space weather, because it really is, it happens in an environment that we do not really live in, and it involves forces that we can't, physically feel other than seeing it. So that's why why I say that the aurora is we naturally experience it with our eyes, but it matters where you are. But to give a little bit of context to my talk here, and I will be getting into some of the more modern science, I'm going to give us a sort of a picture of where we've been. Where did people come up with the science and the knowledge that we know now? Well, we're going to start right at the beginning here with this fellow named Aristotle. And there he is in rock form, I guess, a statue. And he was a giant in scientific thought for nearly 2,000 years. His views, they started in the 4th century BC, and they persisted up until the 1500s. And this is probably one of the more famous things that he is known for, and that is his model of the universe. And based on his observations, what he could see, what he could perceive in nature, is that the sun and the planets, moon, the stars, everything rotated around the earth. And it made perfect sense because we know that there are natural cycles to the seasons, and the sun rises and sets every day, and there's a cycle involved with the moon. So it's all, the universe is eternal, never changing. It's just, and it's static. However, this is all fine and dandy, but could be a problem if you're an ancient and you step outside and you see something like this, and you're really at a loss of words to describe what is going on. And it's really quite unsettling. And this here is showing a so-called blood red aurora, but really the red aurora is, if there is a big solar event, a magnetic storm happening and you're in a low latitude location or far away from the auroral oval where auroras are normally seen, chances are you might see something like this, and like in Europe, and that would be frankly pretty scary. And people of the pre-industrial age, pre-scientific age, they really had no way to describe this except that it was interpreted as an omen of something evil that is going to happen. It could be, divine judgment or famine or war happening. And that's where this picture comes in. This was actually a woodcut from the 1500s. And this came around, just at the time when there really was no science. There were no scientific models to describe what these, lights in the sky really meant. So to them, it really did look like divine judgment. There is fire and brimstone and lightning coming down from heaven. So yeah, auroras, especially events like this, really could be potentially very scary. And traditional cultures, cultures around the world, and not just indigenous North America, but in Europe and in Asia, they associated the aurora with fear, awe, and danger, which could involve death. A more whimsical story, or at least lighthearted story, is this piece of Norwegian folklore where parents warn their children not to play underneath the northern lights, lest they get the hairs on the top of their head burned, because it would provoke the northern lights and they might come down. This is very similar to many, many stories, and the northern indigenous peoples in North America have similar stories. But let's go and start with where did our modern understanding about the aurora come from? And it really had to start with a basic change in our place in the universe. This here is a picture, probably a very famous picture. I can't exactly explain who did it or what era it was from, but as soon as the the geocentric view of the universe fell away and was replaced by a sun-centered view of the universe, a heliocentric view, scientific discovery was able to make more progress. And one of the areas that did progress was our understanding of geomagnetism. And that plays a very important role in the aurora. This year, we'll start here in the 1500s. And yeah, in the 1500s, I should also mention at this time, there was a recognition that magnetism existed, or magnetic materials with magnetic properties existed. And it would that would be like a lodestone or magnetite being suspended by a string, making a rudimentary compass. And people in the 1500s, possibly in the 1400s, knew that they could use it as an aid to navigation. And they always, for some reason, these magnetic materials always pointed north. So I'm going to quickly go over a whirlwind of facts that shows the progression of science as we move towards what causes the aurora. So yeah, in the 1500s, actually in 1600, it was proposed that the Earth is a big magnet. And I guess that would make sense if people had to describe why did these mysterious compasses work. In 1716, you might recognize this fellow, Edmund Halley. He had a comet named after him because he used some newfangled mathematics to predict when this comet would return, and it actually happened. Anyways, he looked at other types of science, and he saw a connection, proposed a possible connection between geomagnetic disturbances and the appearance of auroras. Not much later, a Danish astronomer here, Olaf Hjorter, he noticed that compass needles moved in the presence of auroras. And this fellow, you might recognize his name. He proposed a novel way of measuring temperature, or at least a temperature measuring scale that made sense. He noticed this phenomenon too, but he never published, but Hjorter did. So he got all the credit. Let's move into the 18th century. This was many strides in magnetism and electricity were made during this era. In the 1820s, it was discovered that electric currents, electricity, create magnetic fields. 1830s, Michael Faraday observed that time-varying magnetic fields induce electric currents. And that's really important, as we'll see later when I talk about the auroras in depth. And also, this is how electric generators work. In 1834, Friedrich Gauss, he was a very famous scientist from Germany, did a number of he was involved in a lot of different areas, including physics and mathematics. But in the 1830s, he set up a network of magnetic observatories across Europe to systematically measure and record magnetic data. And this is something that we do even to today. And interestingly enough, when researchers are trying to do doing space weather research and they need to use early data, they can go back to the 19th century and use that data. Like if they wanted to study significant solar event that happened in the 1850s, hint, hint. 1843, the 11th-year sunspot cycle was discovered by a German amateur astronomer who for many years made systematic measurements just counting sunspots. A few years later, another scientist from England, he took that data and then overlaid his own observations about a similar 11-year geomagnetic disturbance cycle, and basically came on to the conclusion that sunspots. Oh, am I hearing myself here? Oh. For some reason, I'm hearing myself echoing back. Am I still there?
You're good.
Yes.
Ian. I think.
Okay, because I actually was hearing myself coming back at me.
Yeah, things were muted. It's good.
Okay, just a minute here. I'm going to go back. I'm sorry. Oh boy, okay, just hold on here a second. Okay, am I, I guess I am not sharing, am I? Am I? Oh, I am, okay.
Yeah, you
Good.
are.
Okay, good. Let's continue on here, okay. So yes, there was an observation that the sunspot cycle correlated with magnetic activity, at least an increase of magnetic disturbances. Not much later after that, there was a big magnetic disturbance that happened in 1859, and many talk about space weather always points to this event in September of 1859, the Carrington event, which basically was a big solar flare, well, a coronal mass ejection that happened. It was detected from Earth by an amateur astronomer who is actually his observations are here in this drawing on the left. He was just observing some rather large sunspots, which then erupted in a blinding solar flare. And 17 hours later, this event manifests itself with spectacular auroras that were seen around the world as far south as Australia and Hawaii. Everywhere aurora could be seen. And not only that, this is the first space weather event that really had an effect on industrial society, because it caused literal damage to the very early communications infrastructure. Not only was it powering or energizing the lines that made up the world's telegraph system, but it was reported that sparks and electric shocks could be were happening at telegraph stations. Fortunately, the infrastructure at that time was still relatively primitive, and that was the extent of the damage. The occasional telegraph office bursting into flames. But it was estimated that if this had happened in the 21st century, the amount of damage that would have occurred in the United States alone was between 600 billion and $2.6 trillion. And we had a close call in 1989 when a CME, or coronal mass ejection, which is really a giant explosion on the surface of the sun, sent a huge wave of charged particles. It hit the Earth and caused something called geomagnetic induced currents in the power infrastructure in northern Quebec, and it caused a fair bit of damage, overheating and melting transformers. And that was in '89. It would be much worse now because our infrastructure is, comparatively speaking, it's older, and we have a lot more space assets in orbit that would literally be fried if there were no mitigation or early warning given. So let's continue on here. Oh yeah, I can go back to this link. But yeah, there's all kinds of videos and things that you can look on online that talk about the sun and geomagnetism. Okay, Kristen Birkeland, he is going to be the last fellow I'm going to talk about, but before we talk about modern auroral or space physics, because he sort of set the tone to where we are now. A fairly remarkable, brilliant researcher in the 1890s. He was the first to recognize that the aurora was related to magnetic storms coming from the sun. And like scientists today, he tried to gather evidence for his hypothesis by essentially doing research, building equipment, building instrumentation, and doing field work. And some of the field work he did was actually rather dangerous. And by 2008, he had enough data to support his view that disturbances in the Earth's magnetic field were driven by electric currents in the atmosphere, in the ionosphere, and that these occurrences in the ionosphere, sorry, they were flowing along the magnetic field lines that make up the Earth's magnetosphere, and they're flowing in and out of the ionosphere. So what he basically stumbled upon were the current systems that we recognize today as powering the aurora. Unfortunately, for many years, his views were rejected by the scientific community. And it took until the space age, until the 60s, that his views were vindicated, and that there actually were currents flowing in the Earth's magnetosphere that described exactly what he was talking about. This is here just a picture of the current systems that we recognize today as what powers or creates the aurora borealis, and that there are many currents, many electric currents that are flowing through the Earth's overall magnetic environment, or I should say at least there's a lot of complex physics that are going on, and it has to do with the Earth's magnetic field lines, and they're all disturbed by the sun. But anyways, this was published in the 1960s, and it was by the 1970s his views were recognized as being for real. And this is our jumping off point to what we understand now is how the aurora actually works. So this here is a nice little picture that was created by our colleagues at UCLA, I believe. And this basically describes where the auroras come from. And we've gone over this before in other talks, but just to reflect, the sun is constantly emitting solar wind, which is essentially the solar atmosphere. It's made up of electrons and ions that are ejected from the sun, and they're constantly flowing towards the Earth. And for the most part, we are protected from a lot of the blast of these particles by our magnetic field, and that's what you see here on the right. If the Earth's magnetic field is undisturbed, it would look like a donut, but because there's a constant flow of solar wind coming towards the Earth, it gets dragged out, especially if there are strong gusts of wind, which come from solar flares and coronal mass ejections. These particles, they collect in the magnetotail, which is the far end, the part of the magnetosphere which is away from the sun. And when there is a magnetic storm happening, if there's been a big solar flare or CME, it will stretch out the magnetotail. And if it gets stretched out enough, figuratively speaking, the magnetic field lines snap, and that releases a flow of electrons as the magnetic field lines reconnect with each other, sort of reconnecting the current system, because these magnetic field lines have current like electrons that are flowing through them. So when we see a typical aurora and this reconnection happens, then that is the mechanism that actually turns on the aurora. And that was something that was discovered quite recently in 2008. It was one of the big takeaways of the Themis mission. And I'm going to go to a video which was created by the Themis people, which maybe more clearly describes what I was trying to attempt to convey. So yeah, you've got the sun, and it's continuously shooting out streams of solar wind, and that solar wind, it is buffeted, or it's deflected by the Earth's magnetic field, but it is stressing the magnetic field, and you can see it sort of peeling away the front of the magnetosphere, and it's pulling it longer and longer. Stretching the magnetic field lines, reconnection happens, causes a flow of electrons down the magnetic field lines, which converge at the north and south magnetic poles. Now, what makes those pretty colors? It basically has to do with the amount of energy that is released whenever an electron, and it will be, for the most part, electrons flowing down along the field lines towards the poles. And depending on the amount of energy released, different color is emitted. But what we mostly see on Earth with our bare eyes when we're looking up in the sky and seeing the aurora, we see a faint green glow along the northern horizon, and it grows, and it can be a pretty impressive display. What that results from is collisions of electrons with atomic oxygen, typically between 100 and 400 kilometers. If you're in a particularly dark region and you have really good eyesight, you may be able to see with your bare eyes a red glow that is a bit higher than the green region. And that is atmospheric oxygen, but at a higher altitude. That will be above 400 kilometers. And sometimes you can see a thin band of red at the bottom of the aurora. And that is actually caused by nitrogen. And that's roughly around, 90, 100 kilometers or so above, well, up to 100 kilometers. So below 100 kilometers is where we can have nitrogen red emissions. And I had to throw in just a few new facts here. This is a recent result from another UCLA mission. It was actually a, shouldn't say student-led mission, but student involvement mission involving a satellite, a microsatellite that actually smaller than a microsatellite, a very small satellite, about the size of a carton of milk, that was built by students. And it was called Elfin, and it had a magnetometer on board, and they recently announced that they observed a different form of electron precipitation that was not emanating from the magnetotail, but actually from the radiation belts. Some of you may be aware that there is a radiation belt that encircles the sun, or sorry, encircles the Earth. And that was actually discovered by America's first artificial satellite, Explorer 1, in 1958. That was the first scientific finding that was announced or came from an American space mission. But anyways, what Elfin reported is that whenever there is stormy space weather, there's a magnetic storm happening, it energizes, or it causes waves to start forming inside of the radiation belts. And it influences electrons that are actually trapped along magnetic field lines. These electrons typically are, bouncing back and forth between the poles, permanently trapped. And they primarily live in the radiation belt. That's actually what the radiation belt is. It's just a magnetically confined region of charged particles. And these waves, when they get stronger because of, say, a CME is buffeting the Earth, injects enough energy into makes the waves energetic enough that if the electron is going in the right direction, it can actually surf all the way down along the wave and hit its destination in the ionosphere. So yeah, that's kind of cool. But this is the kind of science that researchers today are doing in studying the very complex, physics involved in the solar terrestrial environment. This is just one example. And that is what we are doing with our science infrastructure today. We are writing papers using the data we collect from our cameras, from our magnetometers, our radio experiments, to study the solar terrestrial environment, which really involves the relationships between the solar wind, the magnetosphere, and the ionosphere, and I guess also by extension, the sun. And some examples of some spacecraft other than Themis that are studying the sun. Two important ones would be Stereo and ACE and Discover, because they are constantly viewing the sun and giving us a complete view, far side and front side of the sun, giving us early warning when a dangerous solar flare or CME might be coming our way. And that's actually very important. That's space weather mitigation right there. So I'm going to sum up the first half of this talk with this really cool video from the Canadian Space Agency that sort of encapsulates what we've been talking about. It is quite nice. So I should give a bit of a shout out to University of Alberta's website, aurorawatch.ca, because if you go there, you will see our live Aurora camera that we have streaming 24 hours a day of the sky above our space observatory, AUGSO, at Long and Narrow Lake. So yeah, if you're ever interested in knowing what the sky conditions look like, and if there's an aurora happening, you can watch it live from our live stream. Just go to aurorawatch.ca. So I'm going to now go to the next part of my talk, which is on a separate PowerPoint show. So I just have to go and find it. I can find it indeed. Just a minute here. Just going to go right here and start presenting it. Okay, does everybody, Lisa, do you see that okay?
You have your notes on the next slide, so it's not a full screen.
Okay, just a minute here. Just hold on. Sorry about that. That might be better.
Perfect.
Okay. I wasn't sure how long this was going to go. So we probably have seen this picture before, but yes, why do we do space physics research in Athabasca? We are uniquely blessed by having incredibly dark skies and being very close to where auroras happen in North America. Here's a picture of the Earth, and this is where we live. We're in the arguably, colder region of the world, but we are actually reasonably close to the North Magnetic Pole. Just to show you this graphic about what an idealized magnetic field would look like. It is this donut-shaped region of magnetic field lines or magnetic lines of force, and the Earth acts like a magnet, north and south, and the magnetic field lines emanate from the south and enter into the north. And the place on the ends of the poles are the North Magnetic poles. And I've got a picture right there. And that circular region is actually where, whenever there's an aurora happening, there's electron precipitation happening, striking gases in the upper atmosphere, nitrogen and oxygen, making that lovely green and red light. The region inside of this oval is where you are going to mostly see it. That's the northern auroral oval, and we are on the southern tip of it in Alberta. And actually, Western Canada is the most southerly region in at least the northern hemisphere where you can see the aurora. If you were in Europe, you would have to go significantly farther north. And the reason for that is the magnetic North Pole does not happen directly over the geodetic North Pole. There is an offset, and the magnetic pole is somewhere off the northern coast of the Northwest Territories in the Arctic Ocean. So that's why the oval is shifted southward to our favor, which is beneficial because we can set up a magnetic observatory in Athabasca, whereby if you're in Europe, you'd have to go to Siberia or to the northern tip of Norway. So yeah, our location is very easy to get to. So at the time that our geophysical observatory was being built, this is what our surroundings looked like. It was relatively quite dark in the 90s and very early 2000s because there was very little development around the campus. Now, this picture here was taken in 2011, and so it does show some of the development that was starting to take place. And you can probably guess that that is the future home of the multiplex. Now, where are we located? Let me just head over here. That is where our first observatory was placed. Dr. Connors in, I think as early as the late 90s, or at least 2000-ish, set out to build a comprehensive space observatory and astronomical observatory. And he selected this piece of land that was sort of away from, secluded from the main campus, but was still adequately dark. And from what the stories I've been told, it was a profoundly dark part of the campus. So by the time everything was finished in 2004, we had a facility which looked very similar to what we've got right here in the background picture that could study auroral geomagnetism. So there was a magnetometer installed here. We could do auroral all-sky imaging in the main building that has those bubble domes on top. That's where we put cameras that could take pictures all night of the aurora. And we had a robotic telescope, and that was in the dome that you see there to the left. And this was a fairly nice little facility, just 500 meters behind the building. And it was paid for actually by CFI, which is a funding agency in Canada. Here's an early picture of the Geophysical Observatory, AUGO. That was from 2002, I believe. And this is in, I believe it was functional at this time, but it was not yet fully completed. At the time, there was just one dome, and that was to house the one auroral camera, which we owned. And the dome itself is actually quite special because it's made of a type of acrylic plastic that is transparent to a wide range of wavelengths, which is important if you're doing scientifically valuable imaging. Here's some pictures of the completed building when the siding went up, and this is from a video that our campus photographer, Blaze, took a number of years ago in 2004. And this was during an open house. This was before me, but I do remember having taking tours of people through the building. This is Dr. Connors just giving a chat about how the observatory works, I think. Now, one of the things that we did at the observatory, other than do auroral studies, is that we use it as a test facility for new and novel equipment, instrumentation that we often build ourselves. And here, Dr. Connors is working on a home built, or at least a model of a camera that could image meteors that we often get overhead. And this was able to take pictures using a highly sensitive camera pointed at a mirror, and it imaged the entire night sky. And if you coupled this with a camera that runs special motion detection software, with multiple cameras, you can figure out the trajectory of a meteorite and attempt to find its location where it struck the Earth. And we did this for many years, actually. So this is a design that was built in-house. And putting these out at the observatory was just a really convenient place to put new instrumentation. This is just a picture of some of the professional research instrumentation that was brought by the Japanese. By 2007, when I was at the observatory, a second dome was built, and this housed hardware from the folks at Nagoya University. And this is pretty typical for the kind of optical equipment that we have at both of our observatories. In the foreground is an all-sky imager, and it has a special lens that can image, has a 180-degree field of view. And in the background is a special camera. It's actually a 1-pixel camera. It's called a photometer, and it is used to scan back and forth all night, recording light from very faint blue auroras. That it's called an H-beta meridian scanning photometer, and it was used, is still actually being used to measure light from proton aurora. The color of light that come from them is roughly blue, but is exceedingly faint and needs special equipment to detect it. Besides the auroral observatory, we had or still have, a robotic telescope, and this was the first iteration of it. And this also shows one of our first auroral researchers. I was not the first. There was actually 2 that came before me, Ben Warrington and Ian Shelton. And this picture here shows Ian beside a newly completed Newtonian robotic telescope that took the picture that you see right beside us. And our hope with this whole idea with the Athabasca University robotic telescope is it would allow students taking astronomy courses to do their lab exercises with real data that they would take themselves. And when we have students that are taking upper level astronomy courses, they do have the option to use our robotic telescope using the robotic observatory. So this is where we stood in 2010. This is probably what you see if you take the hiking trail or the ski trail behind the university, you will see this. We unfortunately had to move to another location, but I'll get into that in a moment. This is some of the other stuff that we have done for many years. Beside our observatory, we've also been involved in geomagnetic stations across the country, really. And again, the instrument that we use for studying how the magnetic field is affected by the northern lights is by using a magnetometer. This is a picture of a fluxgate magnetometer. It is still in operation right now. It was installed in Fort St. John, BC. And what it does, the business end of the instrument is that tube there, and it's really there to protect the instrument from water and temperature fluctuations. And what we do is we bury them in the ground and we align it to the Earth's magnetic field and make sure that it's perfectly vertical. And then we hook it up into the control electronics like you see on the left. And in most cases, we have a computer connected to the internet, and it's constantly digitizing the data, archiving it, and sending it back to us over the internet. And this is something that we have done really since the early 2000s. All of our magnetic stations follow this methodology. Again, this is an older system, but even some of the newer ones, they look more or less the same. This is just a very different type of magnetometer. This is actually a Japanese one. And yeah, we use a variety of different types of technology to measure not only magnetic fields, but also radio waves. And we'll be getting into that in a minute. This here is a picture of a search coil magnetometer. It's slightly different than the other. So we created, by the time I showed up, there was a fairly expansive network of magnetometer stations across Western Canada. And it was called AUTUM, and that stands for Athabasca University, Themis, UCLA Magnetometer Network. A bit of a mouthful there, but essentially it was the original Alberta magnetometer stations that were joined by other stations in neighboring Saskatchewan, BC, and Inuvik, Northwest Territories, which you can't see. We had a number of different types of instruments, a number of legacy instruments which show up as white dots, and the yellow dots show instruments that were built specifically by UCLA for some of their science or space missions. We had those in, I guess, our more valuable locations, such as in Lethbridge, Calgary, La Ronge, and Inuvik. But still, if you look at, and also I should mention, for many years, we collaborated with Professor Kanji Hayashi from University of Tokyo. He was actually Professor Emeritus, and his hobby as a retired professor was to maintain a network of magnetometers that were left behind by an earlier Japanese space science campaign from the 1990s. And every year he'd come out and just do maintenance on his network. And he produced data and he hosted it from his home. We partnered with him and we were able to share sites, get access to his data, and we offered our services in helping him maintain his network, and we had access to his data. So those were very happy times, and learned an awful lot from him. But still, that doesn't really give us a whole lot of stations for our network, especially if you want to get an accurate picture of the magnetic and electrical environment in the auroral region. If we want to study like the structure of the aurora as you see it, if you're looking towards the northern horizon, you're actually seeing a very complex magnetic and electrical system. And there's only so much you can do with a handful of magnetometers. So Dr. Connors wanted to develop basically a whole bunch of low-cost magnetometers that we could affordably build out our magnetometer network with, and possibly, get some traction that way. This is just a screenshot of our early magnetometer network, Autumn. This is when it still existed only in Western Canada. Yes, PicoMag. These were the proverbial low-cost $500 magnetometers. And we developed this instrument in-house. Dr. Connors did the original conceptual design, I think in the very, very early 2000s, to see if the detectors that we were going to use would work. They did work. And in 2007 and 2008, we set out to build a magnetometer that anybody could install and operate. And this is the business end of it. Looks fairly humble, but it actually did produce reasonable quality data. And the sensors are at the bottom there, these little tubes that you see with wires coming out of the bottom. There's actually 3 of them to measure the X, Y, and Z axes. So we could get a vector measurement of the magnetic field. And this electronics would fit into that tube. And you probably recognize the tube because that's what we traditionally put magnetometers in and bury in the ground. And that is what we did with these. This is just a close-up of the electronics that we designed. We did not design the computer that drives it all, but we were sort of on the cutting edge of technology at the time, and we were designing instruments that now would be considered Internet of Things devices. These are devices that you simply plug them in, they automatically connect to the internet and send back data. And this is exactly what this did. The technology was considerably more primitive and limited to what we have now. But no, this is one of the early circuit boards that we designed in our physics lab. And that we also maintained a website. All of these stations would send back data in real time from multiple locations, and people could log in and select data from pretty much any day that the unit was producing data, and would produce graphs like this. We even presented a poster at a major conference in Earth Sciences, and we were comparing how well our data from our $500 magnetometer compared to a $20,000 magnetometers, and it actually compared quite well, with some caveats. So we were trying to promote it to schools, farmers, landowners, and just amateur astronomers or anybody interested in the Northern Lights. And we were able to get maybe half a dozen units deployed out into the field. And for a couple of years, they worked reasonably well. But while that was all going on, Athabasca was changing. This here is a picture of light pollution over northern Alberta. Just to fill you in with what this means, gray is good, red and white is bad. Our auroral observatory was now in a region that was sort of orangey. It really was not acceptable anymore to do auroral science. Our photometer, for example, could not function in this kind of environment. And this was what was going on. Here's a picture of our site today. It is no longer surrounded by just farmland. There's a number of buildings directly in the way of where we want to look, which is the northern horizon. There's our observatory, and when we're our cameras are pointing or are looking, well, actually they observe all of the sky, but we want to see stuff that's happening over the north. So yeah, as soon as the original observatory was completed and we had instrumentation in place, light pollution was already becoming a problem, starting with the multiplex in 2008, followed by the high school, the Academic Research Center, which is, I guess right here, that was an office building that they built on campus in 2011, I forgot about that. And finally, the new pool. So in 2010, we made plans to get out of town and find a more acceptable location. And we turned to Professor Emeritus Don Cavill to give us a plane ride so we could go and check out some areas that we had identified in Athabasca County. And here's him. I believe he's putting the plane back into the hangar, but let's pretend that he's pulling it out. And so we took to the skies and found this really interesting place. It's actually quite an important place in Athabasca County because this is where Camp Wright is located, and that is the cadet camp, the Air Cadet Camp. It's just between Narrow Lake and Long Lake. And we identified a place near the nearby airstrip, which was actually adjacent to an abandoned Husky oil site, which had a clearing. And out here, it is extremely dark. And it's very unlikely it will ever be developed because it's surrounded by Crown lands. And we got permission to build the observatory there. And that is where the Athabasca University Geospace Observatory has been since 2012. This is what it looked like in 2011 before we broke ground. And this is actually the northern horizon. So this is where our cameras are pointed, or at least observe, every night. And this is where you're going to see auroral structures developing. This is what our all-sky cameras are mostly interested in. This is a conceptual drawing of what the observatory could have been if we had more money. Unfortunately, we had to resort to the more humble shoebox design, but it serves us just fine. And this is just a number of pictures that show the facility as it was being built in the fall of 2011, in September, October, November, and into December. And here the walls are being put up. The second floor is taking form. This roof has been put on. And by February of 2012, the building was ready for habitation, which was a good thing because a couple of weeks later, we had a group from Nagoya University setting up instrumentation and embarking on a very ambitious field campaign. This was headed by Kazuo Shirakawa from Nagoya University. And this is a picture he took in February at the AUGSO site, at the Geospace Observatory site. This is just a picture of the lead up to the campaign. He was going to be bringing over a lot of equipment, some of which is still at our observatory. This is just a breakdown of some of the stuff that was brought over. Of course, the most important thing would be the coats and winter boots. Here's a picture of some of these were the first students that were brought over by Dr. Shirakawa in 2012. And each year he's brought over a group of students to do a week-long field campaign at our Geospace Observatory, with the exception of 2020 and 2021. Recently had a group of students here this year, which was nice to see them again. While this is all happening, there was the opportunity to expand our autumn network, which was mainly in Western Canada, into more, how shall we say, wild territory. We wanted to go to a place where very few have gone before, and we settled on setting up in northern Quebec. There was opportunity for funds from the Canadian Space Agency, who made that video you just recently watched, and we set up 10 sites in northern Quebec. Specifically along the eastern Hudson Bay, and also along the border, at least, near the border with Labrador. 10 stations. We had to do this from start to finish in 11 months. And we, Dr. Connors and myself, we did it. And it was a whirlwind of activity. These sites in Quebec are rather significant for a couple of reasons. One is that they're magnetically conjugate with sites in Antarctica. If you're familiar with the picture I showed earlier about magnetic field lines, they emanate from one pole and end up at another pole. And if you follow some of the magnetic field lines, or if you follow the magnetic field lines at some of the sites along the eastern Hudson Bay, you will find yourself on the continent of Antarctica. That is very unusual, very unique. That is not a common thing. So we were hoping that possibly this would be a jumping off point to partner with an international partner. Unfortunately, maybe they'd be able to build an array in the South Pole. Unfortunately, that never happened. But these sites, our sites are still operational. Maybe someday somebody will take up the challenge. So to get instrumentation for our new network or expanded network, and that's what AutumnX means, we turned back to UCLA, who had built the magnetometers for the Themis mission. They had also built the ground segment instrumentation for the Themis mission, which designed a number of ground-based observatories that were spread across northern Canada. And University of Calgary had an important role in developing these. But UCLA also developed using the same magnetometer, they built ground stations for schools that were to be installed across the United States. We combined these two ideas from these two systems and developed our own ground-based magnetometer system, which we called AutumnX GBO, and significantly simpler, but I think just as rugged. We ship these things out to the sites in northern Quebec, essentially just like you see here. You see there the magnetometer tube. Again, it's a piece of pipe, gets buried in the ground. The electronics are in the box on the left, and we used a much more miniaturized computer that you see in the bottom right. For internet, where we could, we used internet modems that used the cell phone service. And this was something that was just not available a decade earlier. So we were sort of riding on the tails of newly available technology. This is just a few pictures of our first installation campaign when we put in the AutumnX network. And this really is a completely different environment than we'd operated in before. This was in Salouet, northwest, or in the northern tip of Quebec, where the red, if you look at the map on the right, you'll see a red arrow. That is where we put an instrument into, along with all the other spots, all the other sites that have yellow dots. We went to all those places. These are some pictures here of just what the communities look like. In the high Arctic, there is no topsoil, so we had to resort to above ground installations. These are not entirely great, but we didn't really have much of a choice. Here I built a rock cairn in a town south of here. Here's just a picture of what the town looks like inside. We had to resort to installing the instrument in a building because there was nowhere to put it outside, and we couldn't drill into the ground because it was solid rock. This site still works, but one of the issues of putting magnetometers in buildings is that they pick up a lot of cultural noise. And what that means is you pick up every time somebody moves a chair or a table or turns on an electric motor like a fan or a heater, it shows up in our data. Moving south, yeah, this is still the Arctic. Where we could, we tried to co-locate at existing facilities. And here we placed a magnetometer at an Environment Canada weather station. And they, again, same deal, there is no topsoil. They had to bring their own topsoil in the form of sand so they could bury their instruments. We took advantage of that and actually buried the magnetometer in the sand pile that's right in front of the building. Here's just a picture of our setup. We just tried to find a closet where we could put our equipment and then close the door and hope everything works. Field work, of course, can be dangerous. There's always animals and hazards along the way, such as bears or moose and the occasional camel. So yeah, you got to watch out for that. Actually, this site in Saint-Félicien, Dr. Connors set up a station at a local zoo park, which for some reason had camels, but they certainly had animals from the boreal forest. And one of the nice things about field work and setting up our stations, we've been able to engage with the local people and have them involved in the installation and operation of our sites. And these are just some of the people that we met along the way. These folks are from the local astronomy club, and they continue to this day to help maintain and operate our station at the zoo park in Saint-Félicien. And here's just a picture of them after a long day's work, just socializing and talking about how they avoided that dangerous bear and angry moose. Oh, let me go back here. We did have other people who have worked with us in maintaining our array. This here is a picture of technician that worked for our project for a couple of years, Kyle Ryder. He was not involved in the 2014 campaign, but he was around when we were doing maintenance. And here he is doing some installation work on a magnetometer at Sedil. And this is just some of the things we had to do. Sometimes we had to get permission to do, potentially destructive things, but we always cleaned up after ourselves and corrected any kind of damage. Here's me with a shovel, and that was, I believe, a staff member from the weather station. This is actually the weather station at Sedil. And of course, when you're doing field work, besides having a place where to rest your head, you also want to find a place to fill your tummy. And this has always been our go-to restaurant in Schefferville, Quebec, called the Restaurant Blah Blah, where you can get great northern Quebec cuisine like good hearty cheeseburger and poutine and gravy. And yes, I've eaten many of that, and it is definitely tasty if you've been working all day. This is Kyle relaxing with a cup of coffee, but if you're a real Quebecois, you'd have a can of Pepsi with that, which I always had. And when we were doing our installation in Quebec, Dr. Connors helped me. This was a very challenging location because in Schefferville, there is a lot of rock. The soil is very rocky, and this is the result of a day's worth of both of us digging this hole. And this is a victory lap as we completed it here with our pickaxe in hand. Schefferville is known for iron mining, and that's clearly evident just by looking at the dirt. It's very rich in iron ore. That's why the dirt up there, the soil is red tinged, and this is a good example of how we're supposed to bury our magnetometers. We bury everything very neatly so there is no cable exposed, because if there is cable exposed, an animal, typically with very sharp front teeth, is going to find your cable and start chewing. And here's just a picture of me setting up inside the local building. And here's Dr. Connors after a long day's work, looking at, I guess, our formerly clean truck. That's the color of all the vehicles in Schefferville after you drive for a few minutes on the roads. It looks a lot more redder in real life. So I'm going to be wrapping up pretty quickly, but just give you an idea of where we have been heading technologically. All of the stations that we have been developing so far have been tethered to a building, which means that, number one, we are potentially close to cultural noise, and it does limit the kind of installations that we can do. There's a lot of places we'd like to put magnetometers, but we can't because there's no buildings there. And not everybody wants to have holes drilled in the side of their building so we can pass cables in and out of. So we've been looking at developing off-grid magnetometers. We look to what other people in the earth sciences field have been doing, and we look specifically at instrument installations that are put at the poles, because if it can run in Antarctica, it certainly can run in northern Quebec. So we took that approach to try to design an off-grid system, but was similar to the same functionality that we had with our traditional GBOs. And this was an early iteration of it. We ran it for in 2018, and it was definitely experimental. We kind of underestimated how much power these our magnetometers actually use. They actually are a bit power hungry. So we did have to scale it up, but then we ended up with a system that really was quite unwieldy, but not unusual to what people in the community have to do to put instruments out in the field. And it's particularly hard at our latitudes because we don't get an awful lot of sunlight because of our proximity to the pole. We have very long winter nights and short periods of sunlight during the day. Luckily, there was a technological breakthrough around the corner. There was advances in embedded computing modules that were capable of communicating over the cell phone system using mobile internet. And they were far more computationally powerful than what we were using with net picomag. So the system that we designed in 2020 and 2021 was particle mag. And this is just a picture of our lab bench testing out the electronics. So yeah, little devices like this, these are considered IoT computing modules, Internet of Things devices. And they're dirt cheap, and they're very versatile and powerful. And in terms of power, we have developed a system that uses 2 watts of power. So we ended up with a system that is far more manageable and easily deployable, and best of all, can survive running through all of the winter months, specifically December and January. So yeah, we've got, that is where we are right now. We've designed a fleet of these units. We've got 8 in total, and 7 of which are under test at our Geophysical Observatory at AU. And we have another one that is set up in Wabasca. And this is just a picture of me doing some finishing touches this fall, setting it up. And we're hopeful in the coming year that we'll be able to finally get these things deployed after we're finished doing some winter testing, which will be really important. It'll basically prove whether this system is resilient. So that really is the end of my talk, but I just wanted to show you what we have been doing over the last 20 years, 15 years. This is actually the 10th anniversary of our space observatory. And by extension, our geospace observatory is nearly 20 years old. And I guess it really was functional in 2002, so it would be 20 years old. So with that, I guess we're getting a little bit late, but if there's any questions, or if anybody would like to see one Aurora movie, I would be certainly happy to show you that.
Well, thank you, Ian. That was such a comprehensive presentation. It was really, really great.
Yeah. Well, we've done a lot.
Yeah, you have, and you've shown so much. I think we can have an opportunity for some questions. There is a question in the chat that I'd like to open up with, And if people would like to either put questions in the chat or write or just even just talk, it'll be really great. There's a question from Sherry, and she said, when you both, Dr. Connors and Dr. Schofield worked with the University of Calgary, was it the Department of Geomatics Engineering for the magnetometers, and how this would have been addressed by the maritime surface and subsurface, the Mars, and the relationship to the naval community?
The answer to that is we collaborated with the physics department that was specifically the auroral imaging group at University of Calgary with Eric Donovan. And previous to me, I believe Dr. Connors had connections to the physics department at University of Alberta. But certainly when I was on the scene from 2007 onwards, our main collaboration in Canada was with University of Calgary. And they were responsible for managing the Canadian Themis project, which involved all those ground-based Themis magnetometer stations. And they maintain to this day a number of those across northern Canada and the Arctic. I don't believe we've had any connection to the naval community. We have worked on occasion with NRCan, who is responsible for operating the magnetic observatory at Minnook. And we've, on occasion, we've visited them in Ottawa, but that's about the extent of it.
Wonderful. We have a second question. Are these data sets, such as Gauss's 1834 recording of geomagnetic fields across Europe, available as open data, along with contemporary magnetometer data sets from Dr. Connors' research?
Yes, I believe they are. You would go, if I could only remember, to Supermag. Just Google Supermag. They will have open data sets available. I believe they are now starting to open up high cadence data. That means 1 second data or better. It's freely available. Traditionally, it has been degraded because a lot of research groups have not been keen on, giving away their, deluxe edition data without having acknowledgement, or at least having a formal relationship established. But I think things have changed a bit, especially if the data is produced with government money in Canada or the United States. Our policies are that if it was paid for by the taxpayer, the data is open. So Supermag, they collect data from data producers around the world, and they curate it and they clean it, and that's one place you can get it. There are other sites though, and you can actually get it from our site also.
Cool. So Dr. Connors has just added just an extra little bit, saying that the older data is mostly paper graphs. Some of it is being digitized, for example, in the UK, just as an observational thing.
Yeah.
We do have another one. Do we engage local students, Athabasca and Edmonton, in space research using your AUGO to facilities, as in summer camps like they do down south in UCLA?
No, we do not. And it's something I wish we did have. Because our present telescope is set up to allow that with our relationship with the University of North Carolina and the Skynet system, which in the last few years has really expanded into Canada. University of Calgary and Saskatoon are actually on Skynet as well. And what that allows students from everywhere to do is they can log on to the telescope and do observations. But unfortunately, there isn't anything formally organized in Canada to do this, but it is something that we've wanted to do for a while.
But that's
It's just a matter of resources.
yes, of course. Yeah, resources always come into play. I do have a curiosity question right from the beginning of your presentation. You were talking about the aurora borealis in the north. Are there differences between aurora borealis and aurora australis in the south?
No, it's just a mirror image of it. Apparently, what you see in the north is going to be extremely similar to what you see at the south. The difference, though, is your ability to see them in the south. And that's because most of the southern hemisphere is water. And unless you're in the frigid South Pacific or South Indian Ocean, close to Antarctica, you're not going to see anything. Unless, of course, there's something fantastic happening, like just a massive solar event happening.
That's wonderful. So Ian, there were a number of wonderful compliments that have been given from the people that have listened to your presentation. Just an additional thing from Dr. Connors, hundreds of students, mostly in USA and Skynet, that you have been mentioning is that are there tens of summer students employed over the years. So that's just an additional thing.
That is right. In addition to that, it's not only University of North Carolina that use it, but also the US 4-H program, which has quite a good astronomy program. 4-H down there, it's not just farming. You can do really any topic of study that you want to do, they have it. And it's they have a professionally developed curriculum and program that's 4-H participants, they can earn badges or whatever they get.
Oh, that's wonderful. Okay, so
and yeah,
sorry.
No, the University of North Carolina, because we're on the overall Skynet system, everybody has a share of each other's telescope time. And I believe the number is 10%. So when Astro 101 students from University of North Carolina, for example, are doing their lab courses, they log on to the system. And if there's availability in Canada, they're going to go onto one of the systems up here. And we have had a student doing their lab exercises on our hardware. And they've developed the infrastructure to support that.
Oh, that's just absolutely wonderful. Okay, so we have a couple more questions, if you wouldn't mind just responding to. Earlier in the presentation, you mentioned that one of the scientists did dangerous things to collect data for his theory that solar storms and the aurora are related. Can you give us an example of those dangers?
Well, that was Christian Birkeland in the late 19th century. He set up stations across Scandinavia, and these are in very wild lands. Like this is polar bear country. Like this is, in Canada, this would be 70 degrees north and higher. So yeah, this is a very harsh environment, and he actually had a student who died on him.
Oh gosh. Oh dear.
I guess back then grad students weren't worth as much. I don't know.
Oh dear. All right. And so it mentions here too, thanks and to the reference to 4-H program, they would consider that it would be really great to try it with 4-H.
Right. This is specifically the US 4-H. I don't know what they're doing in Canada. It is a bit different. Okay.
And Dr. Connors has just added that with the dangers, the early Scandinavians went up on mountains to prove auroras were yet higher, and Birkeland nearly died in a storm.
Mm-hmm. Yeah, certainly. scientist, he took some extraordinary risks. Not, although Martin did have that experience with the bear too.
Oh dear. Oh dear.
Maybe behind a fence.
Well, thankfully it was a positive outcome there. Well, Ian, we'd like to thank you so much for having such a dynamic presentation. Oh, and somebody would like to see the video, if you wouldn't mind.
Oh yes, I do have a couple things, and this is actually an activity that you can do at home. This is your challenge this winter, and that is to let me just first of all shut this down, to go and photograph the aurora, and you can do it. And the way you can do it is by pulling out your iPhone or your Android. And if you've got, let me just go here. If you've got a reasonably new cell phone, you can get pictures like this. This was taken this fall from my driveway with an iPhone 13. So that's how good cell phones have gotten. But it even gets better than this, and I will show you in a minute. Let me just go back, and I'm going to share a different screen. Okay, can everybody see that?
Yes.
That's a movie. So yeah, all those expensive cameras that we have at the observatory, just a plain vanilla iPhone can make a movie like this. And better yet, that's real time. That's 30 frames per second. Our Japanese colleagues have a sophisticated Sony camera, which can do something similar to this. Now, this isn't, obviously it's not in the same league as a $5,000 Sony low light camera, but this is quite remarkable. So yeah, if you see an aurora happening in your backyard, just grab your cell phone and head outside.
Well, thank you so much, Ian, for leaving us with this challenge. And I hope that we're going to also be able to share all the various pictures and videos that might be generated.
That's what Facebook is for.
Yeah, that's really great. And I'm going to pass it over to Linda. And thank you, everybody, for being here for the presentation.
Yes, thank you. Thank you very much, Lisa. And thank you, Ian. We really appreciate the time and effort it takes to put a presentation like this together. And in closing, I just wanted to mention we lost one of our very huge supporters of science outreach, Albert Carvinen, a week ago Sunday. And I don't know if you guys can see this picture that I'm sharing.
Mm-hmm.
This was taken from a nature walk we did out at their property out at Athabasca Lake. And just as we close, I just would like everyone to think about Albert and just in honor of him as well. Thank you. And Sherry says, thanks for this info, and everyone so much love. Rest in peace, Albert. And in closing, I guess we will log this session off for tonight. Thanks, everybody.
Thank you. Bye-bye.
Bye. Sorry about that, Ian. I wasn't sure how I was going to incorporate mentioning Albert in.
No, actually, that's good. That's actually a nice ending.
Yeah, I just thought in honor of him, I just wanted to mention something.
Oh, yeah, no, that's great.
Yeah.
I'm glad that happens. And I'm glad that I still have a voice.
Yes, thank you so much for everything you did.
Yeah, no problem. You'll have to get Martin to go and do a more scientifically vigorous version of that.
Yeah, yeah.
Maybe talk about space electricity.
Yeah, that would be interesting for sure.
But I think maybe in the past he's done a historical reflections on the science as well. But yeah, it's kind of fun.
Oh yeah, for sure, for sure. And it's kind of nice to have these now that, you know, we record them and they'll be online for people to view in the future.
Mm-hmm. I guess there's 2 other people left.
Oh.
That's okay.
Yeah, so I guess I'll say goodnight and we will chat with you soon.
Okay. Good night,
Okay.
everybody.
Okay, good night. Take
Bye.
care. Bye.